Like there's a formula for Taylor's polynomial in R1, but what's special about that polynomial? This seems like an ambiguous question. What are the derivatives of the Taylor polynomial? What's special about them? As long as you evaluate at A, the Taylor polynomial has the same derivatives as F. That's the point of the Taylor polynomial. So presumably Taylor's polynomial in Rn should have the same property. If you take any derivative, even like a mixed partial derivative of order up to m, you should get the same as if you took the derivative of f as long as you evaluate it. So in order to kind of motivate that, what the polynomial should be, let's figure out how to take derivatives of polynomials in Rn. And this will be easy enough. So let's start with this. So I'll do a lot of things in terms of n-tuples to keep the notation from getting too ugly. Suppose I give you some n-tuple alpha, alpha 1 through alpha n, beta, beta 1 through beta n, of natural numbers or maybe 0. Let's think about the monomial. So here's a monomial, right? It's just a bunch of powers of the variables x. In order to not have to draw something that big every time I want to refer to a monomial, I'll just call that x to the alpha. Right, x is x1 through xn. Alpha is alpha 1 through alpha n. That's what I'll mean by exponentiation. Let's compute d sub beta of x to the alpha. Well, what does d sub beta mean? I mean, take the derivative with respect to the first variable beta 1 times derivative with respect to the second variable beta 2 times, all the way out and up to the n variable beta n times. Do you think it matters if you like permute those d's a little bit? No. We have this theorem about the Clairaut's theorem says the equality of mixed partials. As long as you have a function whose high order derivatives are all continuous, you can permute the order of the differential operators. Is this thing going to have all of its derivatives continuous? Yeah, because I think we can just compute the derivatives. Let's do that. So in order to come up with just a formula, let's compute this. Let's compute the derivative with respect to x1 3 times of the derivative with respect to x2 4 times of x1 to the 7th x2 to the 5th. And let's try to think of it from the inside out. And presumably, I mean, you guys can probably do that basically in your heads. Well, let's think through it this way. So let's take that d2. So I have to take the derivative with respect to x2. So I should think of x1 as being a constant. So what can I do with this x1 to the power of 7? I can pull it out. So I can rewrite that as d1 3 times x1 to the 7th times d2 4 times of x2 to the power of 5. All right, well now let's just do it. What is d2 to the 4th of x2 to the 5th? Yeah, so let's see, if you take one derivative, you'll get 5 times x to the 4th. You'll take another derivative, you'll get 5 times 4 times x cubed. Then 5 times 4 times 3, I lost count. But you know what I'm about to write down. I guess it's going to be like, so I'll end up with 7, so let's deal with this one too. 7 factorial over 7 minus 3 factorial, x1 to the 7 minus 3, times 5 factorial over 5 minus 4 factorial. I know I'm making this look more complicated than it needs to be. But this maybe even tells you exactly what the general formula is going to wind up being. That agrees with what it should be, right? Like that's what happens when you just iterate the power rule. So let's take the derivative of some general monomial. So I guess we can treat like, we could split it up into just a bunch of derivatives applied to single variables one at a time. So what do you get when you take beta 1 derivatives of x1 to the alpha 1?
Yeah, alpha 1 factorial over alpha 1 minus beta 1 factorial times x1 to the alpha 1 minus beta 1.
Yeah. And what will be the thing coming from the x2 term? Be like the same thing.
Always both 2's.
And so on. So in general, we can get like a formula out of this. D beta of x alpha will be, well, I'll try to write these things in order. Alpha 1 factorial, alpha 2 factorial, dot, 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 alpha n factorial, divided by alpha 1 minus beta 1 factorial, and so on, up to alpha n minus beta n factorial, times x1 to the alpha 1 minus beta 1, xn to the alpha n minus beta n. And at least that's what should happen as long as you don't take like more derivatives than there are powers of x. What happens if you do take more derivatives than there are x's? You get 0. And here's what I'll be interested in specifically. Let's think about what happens when I take all of these derivatives and evaluate at the origin. Well, so I guess I'll get 0 whenever this doesn't happen. And apparently I'll get something special when alpha is equal to beta. And let's think about what happens when alpha is equal to beta. When alpha is equal to beta, you get x1 to the power of 0. What's our convention for targeting 0 to the 0 as meaning? Which is a little dishonest, but I mean, it makes things easier. I mean, it is the right formula still. And what if one of these aren't 0? Then you'll have 0 to a non-positive power, which is 0. So most of the derivatives of a monomial evaluated at 0 will be 0. Otherwise, let's see what we get. Alpha 1 factorial, alpha 2 factorial, all the way on up to alpha n factorial, divided by, well, if alpha 1 equals beta 1, then that's what's alpha 1 minus beta 1? 0. 0 factorial is, so the whole denominator there is nice. So there's the derivative of a monomial evaluated at 0. That might not seem exciting, but now maybe we can take the derivatives of polynomials evaluated at 0. In fact, we definitely can, right? Derivatives behave well under addition. But maybe I'll add some notation first. So I'll call an element of the natural numbers union 0 to the power n a multi-index. Because I am treating those alphas like a bunch of indices, right? So I'll call that a multi-index. The order of a multi-index is the sum of all of the terms in that multi-index. And so let's think about if that's even reasonable. If I want to ask you what the order of like x1 cubed, x2 to the 6th is, what would you want to tell me? Because 3 plus 6 is 9. If I what order would you want to call this mixed higher order derivative? 7, because you're taking 7 derivatives in total. 5 plus 2 is 7. So that's why we'll call that the order of alpha. We'll compute sums or differences between multi-indexes by just adding or subtracting. And I'll denote alpha factorial as just the product of all of the factorials of the individual terms. So with that bit of notation, in fact, both of the results from this page become easy to interpret. D beta of alpha raised to the power 0, evaluated at 0, is just alpha factorial if alpha is equal to beta and it's 0 otherwise. And in fact, we can do better than that. I can just write down what d beta of x alpha is for any alpha and beta evaluated anywhere. It should be. Let's take a look. Well, there, that numerator is just like alpha factorial, right? In the denominator, I see alpha minus beta factorial. And on each of these x's, I see alpha minus betas. So I can write the whole derivative now really compactly as just alpha factorial divided by alpha minus beta factorial times x to the power alpha minus beta. Or 0, but it has to be 0. How do people feel about that? That seem okay? So far, so good? It's just notation, right? And it's a bit of notation that gets heavy to keep track of, but without that notation, there would be way more to keep track of. So let's think about derivatives of polynomials now. Let's suppose I give you a polynomial in n variables. And notice I could write that as, right, it should be a sum of a bunch of coefficients next to monomials. So instead of writing all of the x1 to the a1, x2 to the a2, x3 to the a3, because that would just take too much time, I'll write it as p of x is the sum over a bunch of multi-indices of order up to m of some coefficient, c alpha, times x to the alpha. Would you agree that's what a polynomial should be? Just now written in a notation that is pretty compact. Let's take the derivative of these, evaluated at x equals 0. And maybe we'll even figure out what the formula should be, and then we'll go through the proof if there's demand to go through the proof, because if we figure out what the formula is, we'll know what the proof is. Let's take these derivatives. So, no, that's not enough. Well, yeah, there is. Let's try to compute this derivative. So let's see, I want to compute d beta of the sum over a bunch of alphas of c alpha x to the alpha. Now let's see, do derivatives behave well with respect to sums?
Yeah.
Do derivatives behave well with respect to constant multiplication?
Yeah.
So we can push that derivative all the way inside. If you like the fancy one, is I'm using that differential operators are linear operators. If you want the linear algebra language. So that's the same as the sum over a bunch of alphas of c alphas times d beta of x alpha. And now, in fact, let's add in the fact that I want to evaluate at the origin. So let's take a look at this sum. So when we evaluate at the origin, it looks like usually d beta of x alpha at the origin is 0. I can throw out all the terms that are 0. Once I throw out all the terms that are 0, what's the only alpha that contributes a non-zero term to that sum? Say it louder.
Constant.
Well, the one that will be constant after I take all the derivatives. when alpha is equal to beta. So the only term that I actually see, so this is equal to the alpha equals beta term plus a bunch of zeros. And what do I get one for the alpha equals beta term?
Alpha factorial.
Alpha factorial. Though I guess I should call it beta factorial because it's only called alpha when indexed inside of the sum. Nice. And what if I take more derivatives than are there powers in the polynomial? In fact, do you think that you believe the proof just based on the scratch work we did to decide? Should I go through the proof? Okay. No hands are going up for go through the proof. Perfect. Because it's exactly the proof that you think. Right. Use linearity. Use the fact that almost all the terms are 0. But I want something a little bit better than just a polynomial evaluated at x. Right? If you think about what like Taylor's theorem should look like, there should be some x minus a's. I mean, that's not so bad either, right? It should be like the same. If you replace all the x's with x minus a's, but then plug in x equals a, no derivative should change when you just like shift everything rigidly. So we get exactly the same formula by pairing this lemma with the chain rule. If you take d beta of q of x, where q of x is this polynomial, then d beta of q of x evaluated at x equals alpha is beta factorial when you plug in a beta where one of the derivatives isn't 0, and it's 0 otherwise. People feel okay about that? Yeah.
What happened to our sum of C alphas in the last part?
Oh, okay. Oh, god damn it. Thank you. You can't just forget those constants that are being multiplied by things. They change the derivative. They scale it up. Thank you for catching that. Otherwise, I would have gotten deeper into this analysis and said, oh, wait, the coefficients probably should matter. Especially if I want to like find the polynomial which satisfies some derivative conditions at a point. And in fact, let's do that. Let's find the polynomial which satisfies some derivative conditions at a point. So yeah, there should be c betas next to those beta factorials. So let's define the Taylor polynomial. So I want to have a function, so fix a function f which has all of its higher derivatives defined and continuous, close to some point a. Then the associated Taylor polynomial should be a polynomial which satisfies that all of the derivatives up to and including the nth order derivatives are the same as the derivatives of f. So in order to figure out what that has to be, well, let's just kind of write things down. So apparently d alpha of f evaluated at a is supposed to be the same thing. Alpha's already indexing the sum. Is supposed to be the same as d beta of p. I'm going to try to remember I should draw my derivatives with parentheses like that of a. But remember, so for now, let's imagine that there were like a c alpha right there. What is the beta derivative of that polynomial evaluated at x equals a? By thinking about what we computed on the previous page.
Could you repeat that, please?
Yeah. What's the beta derivative of this polynomial evaluated at x equals a? Well, according to that lemma 3, if I have any polynomial that's a bunch of coefficients times x powers of x minus a, then if I take the derivative of that polynomial and evaluate at x equals a, then I'll get 0 if I take too many derivatives. Otherwise, I'll get c beta times beta factorial. Is the polynomial on the next page exactly a polynomial of this form? So what's its derivative when you evaluate at x equals a? Yeah. But I want I wanted to know what polynomial would make this equation be true. So could you take d beta of f evaluated at a equals c beta times beta factorial and solve that for c beta?
Yeah.
Yeah, you divide, right? So that means that this c beta has to be d beta of f evaluated at x equals a divided by beta factorial. So the nth degree Taylor polynomial of a function f evaluated based at some input a is given by p of x equal to the sum of a bunch of things that look like d beta of f. Take beta derivatives of f, evaluate at a, then divide by beta factorial. Cool. And that even reasonably agrees with the Taylor polynomial in R1, right? Like if you're only allowed one tuples, then there's only one tuple of order 1. It's 1. There's only one tuple of order 2. It's the one tuple 2. And so it is the same sum. So now we have Taylor's polynomial, which maybe it's worth writing again so that it can actually be read. Sum over a bunch of alphas d beta of f evaluated at a. Oh, it can't be read because of lighting issues. Oh, god damn it. The sum is indexed by alphas. Now it's reasonable? So now we have Taylor's polynomial. And I suppose that means at this point we're even ready to really appreciate what Taylor's theorem says. So I'm going to flip to the next page and we'll actually just look at Taylor's theorem with a remainder. So here's Taylor's theorem in Rn. Let A be a point in Rn, so this is the point where we're going to center our Taylor polynomial. Let R be bigger than 0, that's some radius. Let's let f be a function that's defined on some open ball. Let's fix some m, so that's how many derivatives I'm going to want to take. And suppose that every partial derivative of f of order m plus 1 or lower. So that's quite a lot of derivatives that need to be defined. But most functions that you'll write down if you just write down a function will probably be infinitely differentiable anyway. Or less are defined and continuous on B. So I need all the derivatives to be continuous so I can use Clover's theorem. Let's let P be the Taylor polynomial of f of degree m centered at A. So that's the thing that was written on the previous page. Then for any point in B, there's some C sitting on the straight line from A to B such that f evaluated at B is the same thing as the Taylor polynomial evaluated at B plus this remainder term. Sum over all alphas of order exactly m plus 1. Take alpha derivatives of f, plug in c, divide by alpha factorial, multiply by b minus a to the alpha. So that looks a lot like Taylor's polynomial and Taylor's theorem in R1, right? the proof is actually just going to appeal to Taylor's theorem in R1. We'll try to come up with a one variable version of this problem, and I think that'll help us motivate what the next thing in the note's going to do. So here's what we'll try to do. So, picture of proof. So, there's the point A where we're centering, oh, God damn it. Let's tone down the brightness maybe. There's the point A where I'm centering my Taylor polynomial. There's this point B where I would like to evaluate the function. The theorem says that there's some point C between A and B, where the difference between the Taylor polynomial and the function itself is given by the derivatives at that point C. So there's like a one variable function that you just see sitting there. How about the one variable function which starts at A, goes along linearly till it makes it to B, and then you take that one variable vector value function and plug that into F. That'll give you a function of one variable with one output. You can apply Taylor's theorem to that. And that's all this proof is going to do. But I guess that means, so I'm going to study the function h of t equal to f of a plus tv, where v is like that vector, the vector that starts at A and points towards B. So I guess that means I need to figure out how to take high order derivatives of that function h and express those in terms of derivatives of f. So I need to understand high order directional derivatives. But that won't even be that bad. Let's compute some high order directional derivatives. Before we compute Taylor's theorem, we need to understand iterated directional derivatives. So here's a proposition which computes high order derivatives of a function that looks like f of a plus tv, exactly the function that I will need to take a derivative of in the proof of Taylor's theorem. So I'll introduce one extra bit of notation. So if I take a bunch of derivatives, a total of m of them, then I will call that a derivative of order m. So if all of the derivatives happen to be nice and continuous, then I can put those in any order I want. Right? Even if it were d1, d2, d1, d3, d1, d5, I could put those in an order so all of the d1s come first, all the d2s come second, all the d3s come third, and so on. In short, I can rewrite it so that it's a d alpha or some choice of alpha. Now let's try to figure out what that choice has to be. And let's do it by just thinking about an example. So let's assume we're in a setting where Taylor's theorem holds. So I guess I need to start with a choice of these I1 through IN. So I don't know, let's take too repetitive there. So let's try to reorder now di1, dim, so that it looks like a d alpha. So that'll be d1, d2, d, d. I think I've written down, I've just put d's in front of all those same numbers. And let's assume we're in a setting where Taylor's theorem applies, so we can permute this to be in any order we want. So how many d1s are there? Is it Paul? How many d2s are there? How many d3s? Cool. So this is the same thing as d alpha where alpha is 4, 2, 2. And let's try to express this number in terms of this tuple. Why was this 4? Where did that 4 come from?
The count of the number of ones.
It was count of the number of ones. So alpha 1 is how many ones are there in I1 through IN. Why was alpha 2, 2?
There's 2.
There were 2 2s. So in general, instead of writing d1, d2, d3 all the way on up through d sub I sub m, I'll write d alpha, where alpha is an n tuple, with alpha j equal to the number of, I don't know, k's, with I k equal to j. Nice. So keep that bit in mind. So I'll wind up with some higher order derivative, and I'll want to express it in terms of a d alpha, and that's how I'll do it. So here's a proposition that's going to compute these higher order directional derivatives. Let's let a be an error n, f be a function defined on an open ball contained in error n, which contains a. Let's assume that all of the derivatives of f of order up to m are continuous. For any v in Rn, I'll define h to be the function in one variable, h of t is equal to f of a plus tv. Then, here's the formula that will compute the nth derivative of f. It'll be given by summing over all n tuples of order m, of m factorial divided by alpha factorial times v alpha. So remember that v is some vector of n numbers, times the alpha derivative of f evaluated at a plus tv. So let's try to prove that theorem. So there's like two mindsets you could have. You could say, well, let's assume that that formula works for the m minus first derivative, and then I'll take one more derivative and try to do the bookkeeping just then. Instead, I'll try to do it all at once by using a combinatorial lemma. So let's write down some combinatorics. So here's here's a combinatorial fact that I'll use. So suppose you have a multi-index, alpha 1 through alpha n, of order m, then m factorial over alpha factorial is the number of distinct ways of permuting a set which contains alpha 1 1s, alpha 2 2s, alpha 3 3s, all the way on until alpha m m's. No, god damn it, alpha n n's. For instance, this means that 5 factorial over 2 2 1 factorial is just the number of distinct ways of rearranging 1 1 1 2 1 1 2 2 3. And I don't know how many people have just already know the proof of this. Let's try to figure out a proof. So it's going to be like some combinatorial thing. So it's going to feel very non-analysis-y. There will be no epsilons, nothing like that. Let's just try to count ways of putting things into buckets. So how should you read this? Let's suppose you have alpha 1 1s, alpha 2 2s, alpha 3 3s, alpha n n's, and you have a total of m spots to put each of them. So here's one way of thinking about it. Let's first pick some ones to put the ones into. So that means I have m places to put a number. I need to put alpha 1 1s. How many ways are there to pick alpha 1 things out of m total? M choose alpha 1. So this will be a little bit informal. So first, number of ways to put in alpha 1s. So that's m choose alpha 1. So now I have m minus alpha 1 spots to put things left. How many ways are there to put in alpha 2 2s?
M minus alpha 1, choose alpha 2.
So I have m minus alpha 1 spots, and I'm going to choose alpha 2 of them to be 2s. And then I'll just keep on going. So
You just slide it down.
oh, yeah. And like, as far as I can see, it's totally invisible, but does it look okay? Okay. Keep on going until you get m minus alpha 1 minus alpha 2 dot 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 minus alpha n minus 1.
You just scoot the paper a little bit.
Yeah. I feel like this classroom must have shifted since last semester, because I remember last semester I could see the board from here. My eyes may have just be broken. There's a lot of space in the back, so it might be bad. Now is not the time to fix it. So now let's just expand this out and see if it walks out to be what we think it should be. What's the formula for m choose alpha 1?
M factorial over m minus alpha 1 factorial.
Yeah, but I'll write it this way.
Okay, times alpha factorial.
Just because I think that's the way that we'll see cancellation.
Okay.
What's the formula for m minus alpha 1 choose alpha 2? And so you wind up with something like that. Do you notice that some things are going to cancel? Looks like all of these will cancel with all of those. And so you're left with m factorial over alpha 1 factorial, alpha 2 factorial, alpha 3 factorial, all the way on to alpha n factorial. And then you have an extra m minus alpha 1 minus alpha 2 minus alpha 3 minus dot 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 minus alpha n factorial. But what was m supposed to be? Yeah, because it's like the norm of alpha. The order of alpha. That's the sum of the alpha ones. So this is also 1. So that's like informal, but that's why it's true. So I'll wind up using this formula a bit. Oh, this is where I was supposed to put the informal argument. Oh well. Okay, so cool. So now let's take a bunch of derivatives. So let's write down some things. So I want to take the derivative of f of a plus tv. That's like explicitly a composition, right? It's f of g of t, where g of t is a plus tv. So let's take the derivative of that. H prime of t by the chain rule should be the sum indexed by something that I'll call k1. It may be weird that the indexing variable has a subscript, but it'll make sense why it does soon. The sum of the, well, let's see. Take a single derivative of f in the direction k1, evaluate at g of t, multiply by dt of g of k upper 1 of t. But what's d by dt of g upper k1 of t? Yeah. So that should be the same as the sum
over all choices of k1 of dk1 of f evaluated at, I'll stick with putting a g of t in here for now. I know what g of t is, it's just this, times v sub k sub 1.
So there's one derivative. Let's take another derivative. So that will become, applying the derivative operator to the only thing that has a variable in it. That should be the sum over all k1s of the derivative of dk1 of f evaluated at g of t. But that's exactly the type of thing we just took a derivative of. So this bit will just wind up being the sum over a bunch of k2s of dk2 of dk1 of f evaluated at g of t times vk2. And then just keep the vk1 because it has to keep on coming. What do you think? Do you notice a pattern in how this is looking? If you take all m of the derivatives, you'll wind up with the sum from k1 goes from 1 to m, k2 goes from 1 to m, k3 goes from 1 to m, all the way until you get to km running from 1 up to m of dkm, dkm minus 1, dot, 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 dk2, dk1 of f evaluated at g of t times the corresponding product of the v sub k's. Everyone pretty happy? And now let's, there was that segue I took at the beginning saying, well, if you see just a bunch of derivatives written like that, you should probably rearrange it so you can write it as a v alpha, as a d alpha. So notice, you can do exactly that. You can rewrite all of this as a d. Did I put the alpha in the subscript or the superscript? I forget which. Apparently in the subscript. So that's d alpha of f, and this is v alpha. Because I could rewrite this as v1, 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 v2, 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 v3, v3, v3. It doesn't matter what order those v's show up in. And here, what am I using? I'm using the fact that I can reorder all those derivatives by chlorostigma. So let's think about what this choice of alpha has to be. And we've kind of already said what it has to be. So if this is d alpha, then what does alpha 1 have to be? Just the number of 1s in these k's. Alpha 2 is the number of 2s amongst these k's. In general, alpha j is the number of, what letter did I use on the previous page? Number of, well, I don't want to use k. Number of j's, number of s's, with k sub s equal to j. Okay, cool. So this is literally now a sum of a bunch of d alphas. But each d alpha is appearing many times. Because in this sum, I'm remembering what order the k's are coming in. Right, when the term 1, 2, 3, 4, 5 would show up as would the term 5, 4, 3, 2, 1. But both of those correspond to the same alpha. They correspond to the alpha that is 1, 1, 1, 1, 1. So here's the question. How many times does any fixed alpha appear in this sum? Now let's think of it. So a single choice of k1 through km will result in that alpha if that k1 through km contains alpha 1, 1s, alpha 2, 2s, alpha 3, 3s, alpha 4, 4s, alpha 5, 5s, and so on. How many ways are there to take alpha 1 1s, alpha 2 2s, alpha 3 3s, and so on, and sprinkle them amongst K1 through Kn?
And choose all.
Well, it's like that's the combinatorial level fact on the previous page. I'm pretty sure it was m factorial over alpha factorial. Nice. So what does that mean? That means I can reindex this sum to just be a sum over alphas, but I need to remember how many times this double counts each alpha. It multi-counts each alpha that many times. So,
2 simplifies to the sum over all alphas, alpha with norm equal to m, of d alpha evaluated at a plus tv, because that's g of t, times v alpha. And now I just need to remember how many showed up. Well, it was exactly m factorial over alpha factorial. Cool.
and on the one hand, like, I'm at time, so I probably am not going to get to the proof of Taylor's theorem, but this feels very deja vu-ish in that I feel like on Monday, I also didn't finish the proof of Taylor's theorem in one period. So I think that there are 2 things that I owe you, and you guys, like I told you, just like stop me at the beginning of class and make sure I did it, right?
Nobody did.
Nobody did. So I feel like this is as much on you guys as it is on me.
I agree.
So here's what I really want you guys to do next time. Unless everyone was just happy with the proof of Taylor's theorem with the remainder. Okay. Then here's what we're going to do. At the beginning of class next time, make sure to remind me, Chris, don't start talking about integration in RN. Finish the proof of Taylor's theorem, and then finish the proof of Taylor's theorem, and then you can do that.